There's a whole range of extra ancillary systems that we can use to enhance the performance of a piston engine, from things like superchargers, carburetors, and fuel injection systems. But what are these systems even used for? Let's find out. Hi, I'm Grant, and welcome to the third class in the AGK series. Today we're going to be having a look at piston engine ancillary systems. And what I mean by that is extra things that we add on to the side of a piston engine in order to improve the performance. Some of these things are essential, like an oil system, and some of these things are enhancements, like a supercharger. Your engine that you're using in a small aircraft might have a combination of all these things, so it's worth learning about how they all work. The 4-stroke cycle is just what it says, it's a cycle, so it's quite hard to define a start point. So we can't just step in at any one stage of the cycle to kick it off. Each of the steps relies on the previous one. So how do we make the engine kick into life then? Well, that's where the starter motor comes in. This is a small external electric motor that is connected to the engine via the gearbox, or in this case a belt or maybe even a chain. It rotates the crankshaft in order to get the pistons moving in the correct motion and starting that suck, squeeze, bang, blow cycle. And once the engine is in the cycle and up to a sufficient speed, the starter motor disengages as it is no longer needed. An ignition system is used to create the electricity for the spark plugs in order to generate those sparks used in the combustion phase of the cycle. Sometimes the ignition system can be the battery, but more commonly used is a magneto system, as this is completely independent of the aircraft electrical system and serves only to generate the electricity for the spark plugs. And normally there's 2 magneto systems in case one of them fails. In order to explain how a magneto works, we need to have a look at some electric stuff, which we're going to cover a lot more in the future of this series, so don't get too bogged down if you don't understand the concepts fully yet. Hopefully you will when I release future videos on the electrics side of things in AGK. So the first thing we need to do is to generate an electrical current, and we can do this by passing a magnet through a coil of wire. Think of the magnetic field around the magnet interacting with all the little electrons inside the wire and pulling and pushing them along to create a flow of electricity. If we move it in and out of a coil of wire, we would have an alternating flow of current, or AC. We can also achieve the same effect by just rotating a magnet near a coil of wire, and the magnetic field will spin and pass over the length of wire, pushing the little electrons along, and as the other side of the magnetic field passes over the coil, then they will pull the electrons back along and the current will flow the other way, again producing AC electricity. So what we can do is we can attach some sort of spinny thing like the engine to this magnet to make it go round and start to generate electricity, which is what we want. So that's the first stage of the magneto system, is generating a current. Another thing located in a magneto is called a transformer. This is a cool and quite clever electrical component that increases the voltage. If we have an AC current flowing through a wire and we place it next to another coil of wire that is separate, then as the current flows along the wire, it creates a magnetic field which is constantly pulsing and switching directions along with the magnet that is generating the electricity in the first place. This magnetic field influences the electrons in the unconnected wire, therefore causing a current to flow in that wire. If we increase the length of the unconnected wire that is going to be influenced by this magnetic field, then it stands to reason that we will get more electrons pushing and pulling along this wire, just purely by a factor of there's a longer bit of wire, there's going to be more electrons in it. This is a method used to increase the electrical push force, purely by a fact that there are more electrons in the longer length of wire. That electrical push force is otherwise known as voltage. And this is clever because it lets us have a very low output voltage from the generation side of things and then step up the voltage using a transformer. So after we've got that high voltage, we want to send it towards a spark plug to create the spark, obviously for the combustion. But we want to do it in the most efficient manner possible. We would not want to have one of these magnetos for every single spark plug, because it also would lead to the potential for failure of those systems. So what we can do is we can use something called a distributor. And a distributor is essentially a spinning switch. So the distributor spins round, making and breaking the circuits with all these spark plugs, and does it in the correct timing and the correct order in order to make these circuits send the electrical signal to create the spark and then move on to the next one, and so on in this cyclical fashion. And that's the three systems that make up a magneto. You've got sort of the generation side, the transformer bit to step up the voltage, and then the distributor to send the voltage where it needs to go to which spark plug at the correct time. The moving parts of the engine must be lubricated to reduce friction and heat buildup. So we use an oil system for cooling and lubrication. The type of oil we use is important as we operate these engines at a large variety of temperatures and pressures as we climb and descend through the atmosphere. So if it's too thin, it can flow around the components too easily and not have enough time to draw away the heat from the components as it runs over them. And conversely, if it's too thick, then it will be very hard to flow and it might not get to all the components that need the cooling or lubricating effects. Therefore, it's important that we use a fairly stable oil that maintains the correct viscosity so it can flow well at all phases of flight. Generally speaking, there are two types of oil system. You've got dry sump and wet sump. In a dry sump system, which is what this is, the oil is drawn from a tank by an engine-driven pump. The pump will have a variable output pressure depending on the engine RPM. The pump will also have a filter just before it to remove any of the small metal particles or other contaminants in the oil that could break the pump. These filters are replaced periodically, and it's much cheaper to replace a filter than a pump, which is why there's these filters in place. So after the pump, the oil is delivered to the engine components that need it and sprayed over it essentially. And these components are mainly the crankshaft, the camshaft, and the pistons. And after the oil has done its job of cooling and lubricating, it naturally runs down the engine because of gravity and collects in the sump, which is like a bucket underneath the engine. The oil that is collected here is then scavenged by a scavenge pump. This is also an engine-driven pump, but more powerful than the normal oil pump, as this ensures that the sump remains dry. There's also a filter here, and as the used engine oil passes through the scavenge pump and makes its way back to the reservoir, it goes through an oil cooler, which is a component that has a lot of chambers in it that the oil fills. The chambers, or sometimes known as fins, have a lot of surface area that are exposed to air passing over the outside of it, and that takes away the heat and cools the oil down before it returns to the tank. It's basically a very simple ridged structure, I think would be a way to describe it, and the oil fills up these ridges and air passes over the ridges and the air cools the oil that is contained in those ridges before it heads back to the reservoir. And these ridges, these fins you might call them, are used throughout the engine where the temperatures get high. You might see them on the outside of the cylinders, for instance, and that just allows lots of air to get in about and take away heat from those components. And in the system as well, there's various pressure relief valves if things get too high pressure, and gauges to measure oil temperatures and pressures as well, but I've just not drawn them for ease of simplicity and understanding. So in the other type of system, a wet sump system, we use the sump as the tank, and that basically eliminates the needs for a few components like the scavenge pump, the oil tank, and all the associated oil pipes or oil lines that are used to move the oil in and out of these components. The crankshaft will also rotate slightly into the sump, picking up oil and splashing it around the engine as it rotates. This means that the system saves weight, which is very, very beneficial for aircraft, but it can lead to excessive splashing of that oil at high RPMs, which can mean that the engine oil can overcoat the engine if the aircraft flies at high angles or negative G-forces as well. So you've got the high RPM splashing everything around. If you get high angle, then gravity would pull the oil over the engine, maybe a bit too much, And if you're flying at negative G-forces, that basically means that the oil will come out of the sump and maybe lead to too much oil in the system. But both systems, wet sump and dry sump, will have their uses, and your aircraft will have one or the other depending on what manufacturer has designed it and what they think is most appropriate for the plane you're flying. The fuel used in piston engines is called avgas, aviation gasoline, which is standardized and has a few additives in it to help with the consistency of the combustion in the cylinder. The fuel to air mix that gets combusted in the cylinders is also very important. You need to get the correct ratios. If the fuel to air mixture gets too hot, it can detonate instead of combust. And this is when the fuel ignites and burns too quickly, which releases all of the energy suddenly and can overstress the engine. We therefore need to control the combustion so it's consistent and doesn't risk this explosive detonation. The chemically correct mixture for fuel to air is about 15 parts air and 1 part fuel, but this comes with the risk of detonation. So what we can do is we can add or reduce the amount of fuel in the mixture. When we add fuel and make the mixture richer, then the excess fuel that isn't used for that chemically correct combustion is used to cool the cylinder instead. The excess fuel absorbs the latent heat and brings the risk of detonation down. This is very useful at high power settings like at takeoff, because you don't want to risk having detonation, unstable engine characteristics at this point in flight. So you might increase the richness by about 30% compared to the normal ratio. This has the disadvantage of burning more fuel though. This is why we can also reduce the amount of fuel or lean out the mixture. If we're in the cruise, for example, with lower power settings than takeoff, we can lean out the mixture and fly with maybe 20 to 30% less fuel in the mixture. You may think that this will result in the combustion heating up, because it's the opposite of what we've just said. We don't have the excess fuel to absorb the latent heat, but it doesn't. This is because by adding less fuel, the combustion is slower and there are simply fewer molecules of fuel creating that heat. Careful control of the mixture can be used to optimize the engine for various phases of flight through the use of a carburetor or a fuel injection system. Carburetors are complicated bits of kit, so this will be a fairly simple overview of how they work. Basically, the carburetor controls the amount of air added to the fuel to create the correct mixture ratio using airflow principles and no electricity at all. So how does this work then? So the fuel is delivered to this chamber by an engine-driven fuel pump further down the line, and this chamber and a U-bend fill up the fuel to a certain level. If the engine is off, then both the levels in the chamber and the U-bend will be at the same level. When we switch the engine on, air is drawn up through this pipe called the choke. And as the air travels through this narrowing part here next to the nozzle, then Bernoulli's theory tells us that the static pressure of the air drops. This low pressure area causes fuel to be drawn up the U-bend and sprayed out by the nozzle into the air to create the mixture of fuel and air delivered to the engine via the throttle. If we want to adjust the mixture, then we have a mixture control valve connected to a lever in the cockpit, which regulates the amount of ambient air let into the chamber and the U-bend so that either more or less fuel is pulled up by the low pressure area in the choke. For example, if we kept the pressure in the chamber high, then the low pressure area will draw more fuel due to that pressure differential. Then if we want to draw less fuel up, we can reduce the pressure in the chamber, and that's a lower pressure differential. There's various other components in a carburetor which will improve the performance that would be useful to know, but I'm not going to cover in this class. I would encourage you to go and look at carburetor videos for more detail. Another way to control the mixture, and used on more modern engines and diesel engines, is a fuel injection system. This is a very simple system to understand, and it's an updated solution to the carburetor. These are electronically controlled nozzles which spray in just the correct amount of fuel, either into the air intake before it enters the cylinder, which is called indirect, or spray directly into the cylinder itself, which is called direct. The lever in the cockpit you move to tell the engine, how much mixture you want will be connected to a computer, and the computer will regulate how much fuel is sprayed into the cylinder, or indeed before the cylinder if it's an indirect system. One of the problems with a piston engine is that as we climb the aircraft to a higher and higher altitude, the density of the air decreases. This means that there are fewer and fewer oxygen molecules in the air to react and burn with the fuel as we climb. This means that the combustion is less powerful, and as the aircraft climbs beyond a certain altitude, the power starts to fade away for a given throttle setting. To counteract this, you can open the throttle more, allowing more air and more fuel into the cylinder as you climb. There does, however, reach a point where you're at full throttle and you can't let in any more air and fuel into the cylinder. For example, at about 20,000 feet, a normally aspirated engine will have lost about 40 to 50% of its power. You see I said normally aspirated there, which means it's just getting the air drawn in without the use of something called a supercharger. So what is a supercharger then? Well, this is a device that is placed after the carburetor that compresses the fuel and air mixture so that the mass of the air in the cylinder is artificially raised and more power can be gained, which adds a few extra horsepower. This can be done a couple of ways. The first is called ground boosting. This is where the maximum power of the engine at sea level is boosted. For the same engine, the overall horsepower is higher, and therefore the drop-off that occurs with altitude isn't as drastic. You can see at 10,000 feet, we've still got roughly the normal power that we would have in a regularly, normally aspirated engine, just by boosting that ground level with the same drop-off. It's just adding more, same drop-off, you're going to get more when you're high up at altitude. The other way is called altitude boosting, whereby the supercharger is tuned to a specific altitude so that it provides its maximum boost and power increase at the rated altitude. This means that the amount of boost slowly creeps up as we reach the altitude, then it drops off in the same way as both the ground boosted supercharger and normally aspirated engine do after that point. This means that it can be tuned for a specific cruise altitude, engine RPM, and other various factors to provide the most power for cruise, for example. This may provide more power than necessary for that altitude, RPM, etc., than in a normally aspirated engine, which therefore allows lower power settings to be used, which can help with fuel burn and engine wear. If we can run an engine 80% of its max output rather than 100%, then it's going to be good for the engine through the use of a altitude boosted supercharger. So that's what a supercharger is used for, but how does it work? It essentially uses gears from the engine and the gearbox in order to turn something called an impeller. An impeller is a device that squeezes a gas by rotating it very quickly and forcing the gas out of the center because of centrifugal force. And as it reaches the edges, it enters something called a diffuser. And the diffuser slows the gas down slightly, trading dynamic pressure for static pressure. And when the static pressure suddenly increases, so too does the volume and temperature. And this is the gas that is then sent to the engine. With more pressure, it means there's more oxygen and there's more volume of air there as well. So that means that there's going to be a better combustion when that air and fuel mixture enters the engine. Another way to do the same thing is through something called a turbocharger. This uses the same impeller process to increase the pressure, volume and temperature, but instead of using gears from the engine, the supercharger uses the exhaust gas from the engine to turn the impeller itself. The exhaust gas is hot and therefore the impeller gets hot, and this means that we can't compress the air and fuel together that we might do in a supercharger, because the compression might cause the temperature to rise too high and cause a combustion before the fuel is even entered into the cylinder. So what we do is we simply compress the air on its own, then add the fuel in, and it gets basically the same effect. The advantage of a turbocharger is that it doesn't use a big heavy system of gears and all that sort of stuff, so it's more lightweight. But because it's relying on the exhaust from the engine, there's a bit of what we call turbo lag. As the engine gets up to speed, and the exhaust coming out the back is fast enough to make the exhaust gases spin the impeller at the correct speed in order to draw in the correct amount of air and compress the correct amount of air. To summarise then, a few ancillary components on a standard piston engine would be things like a starter motor, which is used just to start the process off, an electrical motor that starts the cycle, starts the pistons moving in the correct direction until the speed of the engine and the process is going. Then we can disconnect the starter motor and the engine runs itself. We get the ignition system, which is used in the form of a magneto system. We basically spin a magnet and it induces a flow of electricity back and forth in a coil of wire. This coil of wire creates a magnetic field which interacts with another coil of wire which has more length of wire that is going to be affected by that magnetic field. This means a higher voltage. Higher voltage is good because it helps create sparks in the spark plug, and a distributor is a spinning switch that sends the voltage to the spark plugs at the correct moment and means you don't need loads and loads of magnetos. You can distribute it to all the spark plugs in all the cylinders at the correct time. We've got oil systems. Oil systems can be either dry sump or wet sump. This is an example of a dry sump. We've got an oil reservoir that contains the correct viscosity oil that we need for flying. It is sucked up via an engine-driven pump. Before that, it passes through a filter. Filters are good because they get rid of any contaminants in the oil, and those contaminants might damage the pump. It's much cheaper and easier to replace a filter than it is to replace a pump. So after the pump has sucked up the oil via the filter, it delivers it to some sort of spraying system, and these nozzles spray oil over the engine, coats all the components that need it, the cylinders, camshaft, crankshaft, and the oil drips down and collects in the sump at the bottom, which is like a little bucket. The sump is then dried via a scavenge pump and another filter, and on its way back to the engine it goes through an oil cooling system, basically something with loads of chambers that fill up with oil, and these chambers are easily exposed to the air, and the air passing over it cools it before it is returned to the oil reservoir. If we have a wet sump system, we basically eliminate the need for this reservoir, and all the oil is housed in a sump at the bottom. It will probably be a lot higher and a lot deeper because the crankshaft actually rotates in the sump and it splashes oil around the engine. Both have their uses in aviation, and your aircraft will probably have one or the other depending on what the manufacturer thinks is most appropriate. Fuel mixture is very important. If we have a rich mixture, it can help to cool the engine, but comes with the trade-off of burning more fuel. And if we have a lean mixture, it is very good for fuel efficiency, and we don't have to, and those situations where we don't have to use maximum and all the power that the engine can give. The way that we control the fuel mixture is maybe through a carburetor, which is a clever system using Bernoulli's theory to create a low pressure area above the nozzle and draw fuel into the choke and via the throttle towards the intakes of the engine valves, essentially. We also have a mixture control valve, which will basically control the ambient pressure in the little sort of fuel reservoir and the U-bend, and if we create a higher pressure here, then it's going to be more fuel sucked up, and if it's a lower pressure here, it's going to be less fuel sucked up by the Venturi tube and that Bernoulli's theory that we talked about. Another way of delivering fuel is doing it via clever fuel injection systems, which are basically electrically controlled nozzles which will spray just the correct amount of fuel into the engine cylinders or into the air intake before the fuel air mixture reaches the cylinders, and it's usually computer controlled and very clever bits of kit, quite common in normal modern aircraft. Another thing you can do with this air and fuel mixture is you can compress it. This will delay the effects of reducing power with altitude, either by ground boosting, is basically giving us more power to start with, which causes the reduction to be less drastic with altitude, or you can tune it so that it provides just the right amount of boost at a set altitude, RPM, temperature, etc., and that way you get the most fuel effective and best combustion at a certain altitude, therefore giving you way more power at that altitude. And if you don't need that power, you can operate the engine at 80% of its normal full capacity, and that means that it's good for fuel efficiency, engine wear and tear, etc. And a supercharger is normally used to do this, and it is controlled via gears or something from the engine. Or you can get a turbocharger, which runs off the exhaust gases flowing over it like a water mill or something. It turns the turbocharger, which is connected to an impeller at the front, which sucks up air, just air in a turbocharger, compresses it before you add fuel.